Welcome to lesson 8.2.3, scientific notation with negative powers of 10. So today we're going to work on scientific notation again, but we're going to look at scientific notation when our integer is a negative power and how that gives us small, very, very small numbers, okay? So in here, we're going to take a look at a typical human hair that has a diameter of 25, let's see, tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millions. Wow, 25 millionths meter. So instead of writing that number out like that and doing what we just had to do and going through and counting the place values, we're going to go ahead and write it in scientific notation. Now, we know that when we have positive powers, as shown in our table here, when we have positive powers, that tells us how many spaces to move the decimal to the right because our number is going to get larger. In this case, though, we want our number to get smaller. So if we look at the number that we're working with, instead of moving our decimal, now this is where it gets confusing. Typically, when we have our numbers, so if we had 235, our decimal would be here and we would move it to the left. But if you look at this number, the 25 millionths, here's our decimal, and to create a number that's between 1 and 10, we have to actually move it to the right. So because we're moving that decimal to the right, that means our number is going to get, essentially it's getting bigger so it can get turned into a whole number, so that way when we multiply it by the exponent, which is going to be negative, it can get smaller. Again, very confusing when you're talking through it. When you figure out the process and just keep working through it, very simple. All right, so here, if you take a look, if we have 2 and 345 thousandths and we multiply it times 10 to the negative first, instead of moving our decimal to the right, it moves to the left. It's like we're dividing it by that power of 10. Okay, so here, when I moved, so if I look at this column, I'm moving my decimal to the right 3 places, so this is times 10 to the third, because the decimal is moving to the right to get it out of scientific notation. Here, if we're getting it out of scientific notation, we're moving it 3 times to the left, so it would be a negative 3. All right, so here, so for the first part, we want to move the decimal point to the right as many places as we need to get it between 1 and 10. And I know, so just looking at my numbers, I know that I'm going to get 2 and 5 tenths. That's how far I have to move it. Okay, so then we're going to divide 25 millionths by my answer. So I'm going to take 0 and 0, 0. How many are there? 4. So 1, 2, 3, 4, and then 25, and I'm going to divide it by 2 and 5 tenths. And when I do that, I get an answer of 1 millionth. So 0, and then 1, 2, 3, 4 zeros. 2, 3, 4. Okay. So then what that means is if I'm going to write this as a power of 10, it can't be 10, so I have to move the decimal 1, 2, 3, 4, 5 places. It can't be 10 to the 5th because it's so small. It has to be 10 to the negative 5th power. So then, if we want to represent our number in scientific notation, it would be that 2 and 5 tenths times 10 to the negative 5th power. So it's the same idea as when we're working with those positive powers, but in this case, because we're getting a smaller number, that exponent becomes negative. Okay? So when you move the decimal point, how can you know whether you are increasing or decreasing the number? Okay, so when you're moving the decimal point, if you move your decimal point to the left, so moving the decimal points makes the number smaller. Moving the decimal point to the right makes the number bigger. Okay, so when we're taking that decimal and moving it to the right, our number is getting bigger, and when we take that decimal and move it to the left, it's getting smaller. Okay, so then explain how the two steps of moving the decimal and multiplying by our power of 10 leave the value of the original number unchanged. Well, again, like when you're anytime you're multiplying by 10, so even if I take 6 times 10, I still keep that 6 and I'm just adding that 0. Even if I do 15 times 10, I keep that 15 and I add that 0. All that's happening is that my decimal is moving. So because of the fact that my decimal is moving, it's just adding more zeros, not any number 1 through 9. Okay, so by multiplying by that power of 10, it's just increasing or decreasing the number by a power of 10. So here, this only increases or decreases the number by a power of 10. And that's why it doesn't change, because it's only the decimal that's moving. And when you move that decimal, so here, like let's say I had 15 times 100, so I would have 15 and that decimal would be here, and I would move the decimal 2 places, which would give me 1,500. So we're not adding numbers 1 through 9. When we move the decimal, we're only allowed to add zeros. Okay, so the average size of an atom is about, so again, tenths, hundredths, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, about 300 millionths of a centimeter across. Write the average size of an atom in scientific notation. So my doing word is that I'm writing it in scientific notation. The question, there is no question, it's just telling us what to do, but the number is 300 millionths. Okay, so 300 millionths. So step 1, we are going to move the decimal point as many places as necessary to find that number between 1 and 10. So first we're going to place the decimal point. Once we place the decimal point, oh, there we go. Once we place the decimal point, we get 3 decimals 0. Okay, so we've moved it now. 3. How many zeros? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, and then the 3. So 1, 2, 3, 4, 5, 6, 7, 8. And that's what we get for our decimal. So then now in step 2, count the number of places you moved the decimal point. In this case, we moved it 8 places. Step 3, multiply 3 times the power of 10. And in this case, that power of 10 isn't going to be 8, it's going to be negative 8. Because we don't want this 3 to get bigger, we want it to get smaller. Okay, so since 300 millionths is less than 1, we move the decimal point to the right, and the exponent on the 10 is negative. So the average size of an atom in scientific notation is 3 times 10 to the negative 8. Write them yourself. All right, critical thinking. When you write a number that is less than 10, that is less than 1 in scientific notation, how does the power of 10 differ from when you write the number greater than 1 in scientific notation? Well, again, the difference is because the number is smaller than 1, the exponent of the power of 10 is negative. That's what should tell you or should imply that your number is getting smaller. Okay, and if you have a small number, that's what tells you that your exponent should be negative. So when you see that you're working with a number where the decimal is in front of, so where you're working with a smaller number and the decimal is in front of what could be your whole number, you know your decimal has to be, or your power has to be negative. All right, so I want you to go ahead and pause and try each of these on your own, and when you come back, we'll check your answers. All right, so here you should have gotten 8 and 29/100 times 10 to the 1, 2, 3, 4, 5. So 10 to the negative 5th power. Or, I'm sorry, 10 to the, 10 to the negative 5 power, or 10 to the negative 5th power. And then here you would have gotten 3 and 2/100 because you still have to keep these two numbers there, so when you expand it, they stick on the number. Times 10 to the, you moved it 1, 2, 3, 4, 5, 6, 7. So 10 to the negative 7th power. A typical red blood cell in the human blood has a diameter of approximately 7 tenths, hundreds, thousands, 10,000s, 100,000, so 7 millionths of a meter. Write the diameter in scientific notation. So yes, you should be doing your close reading, and you should have gotten 7 times 10 to the negative 6 meters. Yes, you could also have 7.0 times 10 to the negative 6. That doesn't change the exponent, but again, 7 is the same thing as 7 and 0 tenths. Okay, so now we're going to work backwards. So platelets are one component of human blood. A typical platelet has a diameter of approximately 2 33/100 times 10 to the negative 6 meter. I want to know how small that actually is, so I'm going to go ahead and I'm going to write it in standard notation. Remember, standard notation is how we typically see numbers. So we're taking this number here and writing it in standard notation. So the first thing that we are going to do is we are going to use the exponent of the power of 10 to see how many places we have to move the decimal point. Well, it's a negative 6, so since the exponent is a negative 6, I want to move it 6 places. However, since it's a negative 6, I'm moving it 6 places to the left. So 6 places to the left. Okay? Place the decimal point. Since you are going to write a number less than 2 and 33/100, move the decimal point to the left. So if you wrote this up here, you do not need to write the from since to the bottom. Okay? So then in this case, our answer in standard notation would be 0 and 1, 2, 3. So tenths, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions. So it'd be 233 millionths. All right, so explain whether 9 tenths times 10 to the 5th is written in scientific notation. If not, write it correctly. So real quick, I want you to decide, yes, it's in scientific notation, or no, it is not. If you said yes, it is, my guess is that you just looked at the fact that it had this. Yes, you need to have that multiplication of 10 to a power. However, that first number has to be between 1 and 10. Is 0 and 9 tenths between 1 and 10? It's not. It's actually smaller than 1, so I have to move that decimal one more time to the right. Since I have to move it one more time to the right, that means my exponent is going to go from a negative 5 to a negative 6. Okay, so in justifying my answer, we can say no, because 0 and 9 tenths is not between 1 and 10, so the decimal needs to move one more place to the left. I'm sorry, right. This would make the exponent a negative 6, not a negative 5. Okay, so then in this case, you would have 9 times 10 to the negative 6. So now, which number is larger? 2 times 10 to the negative third or 3 times 10 to the negative 2? In this case, you can't just look at your whole number because of the fact that you have it multiplied by a power of 10. So let's look at this logically. If I have to move this 3 places to the left, that means that this 2 becomes 1, 2, 3, becomes 0 and 2 thousandths. This 3 has to move 2 to the left, so it becomes 0 and 3 hundredths. And when we compare them, we know 0 and 3 hundredths is larger, so I know that 3 times 10 to the negative 2 is larger. Again, you can just compare exponents. If whatever exponent is larger, that number is going to be larger. So since negative 2 is bigger than negative 3, we know that 3 times 10 to the negative 2 is going to be the bigger number. Now, if my exponent is the same, then I have to look at my whole number. All right. So again, 3 times 10 to the negative 2 is bigger because the exponent is larger. All right, now you have the opportunity to try 3 of these on your own. Don't forget to do your close reading. When you come back, we're going to check your work. All right, so number 9, you have 1 and 45 thousandths times 10 to the negative 6. You should have gotten 0, decimal. 1, 2, 3, 4, 5 zeros. So 1, 2, 3, 4, 5, and then your 45. I'm sorry, I missed the 1 in the 0. 1, 0, 4, 5. Okay, so again, if I actually do the work, I'm moving it 6 places, but I'm moving it 6 places to the left. So 1, 2, 3, 4, 5, 6. Okay, and since I had one number here, that means I have that many zeros. So another way to look at it is, since I'm moving it 5 places, that tells me I need to have 4 zeros and then my numbers. So you should have gotten 0 and 99 tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millions. So 99 millions. And then here you have 10, or 1 times 10 to the negative 2, which would be 0 and 1/100th of a meter. Okay, so here we measured the length of the ants. It's 1 times 10 to the negative 2 meters, and we're writing it in standard notation. All right, so the next thing that you are going to do is you are going to do your guided practice problem. You're going to go ahead and do all of them. And as always, if you have any questions, please be sure to write them down or email me so we can go over them in class.